have all the phones that are manually transcribed, and according to the person, the transcriber, we can classify the native productions into either correct or incorrect pronunciations. For those that are labeled correct by the manually, we can then compare it with the machine's output, the computer's output, and then come up with true acceptance, false rejection. And those that are mispronunciations, we can come up with false acceptance and true rejection. And then we can focus on the true rejections and look at the ability to diagnose those phonetic errors. Now we summarize this into two numbers, the detection accuracy, which is basically this addition of true acceptance and true rejection, normalized, and also diagnosis accuracy, the percentage of correct diagnosis. However, after all this work in ERN, extended recognition network generation, using about 200 rules, we were only able to achieve a detection accuracy of about 76% and a diagnosis accuracy of about 43%. So we feel that we need to do something different, okay? So when we review the ERN approach, we know that manually authored rules may not anticipate all the mispronunciations that can occur. Data-derived rules are limited to the training data, the observations in the training data. And also sometimes we have to prune the phonological rules because then our ERNs become too bushy. However, the mispronunciations that are missing from the ERN can never be detected or diagnosed. And furthermore, we actually separate the generation and the training of our acoustic models and our phonological rules, so they're independent, and then contextual information is lost. So what we feel that we need is a tighter integration between acoustic models and phonological context, leading to better phone recognition. So it is at this time that we have the onset of deep neural networks, and this is the doctoral work of my former student, Dr. Li Kun. And he started doing free phone recognition using a deep neural network and having state-level acoustic models and state transition models. And then he can formulate the target function of Viterbi decoding as such here. So this is the state acoustic models and the phone state transition models. And then also this is the diagram illustrating the Viterbi decoding. So here's the state acoustic models and the state transition models. Now, if we look at the illustration for ERN, then basically we see the disjoint between the acoustic model and a phonological model. So what we want to do is to replace that with something, and eventually it became the multi-distribution DNN. And we also want to be able to provide some phonological context, so we decided that we will align the canonical productions with the signal to get a Q-dict. Okay, Q-dict I'll illustrate a little bit more in a moment. And so then we can get the phone state posteriors with this context, and the Q-dict is actually a 7-gram, the current phone, 3 previous and 3 subsequent phones, and then we can replace the Viterbi decoding with this function, okay? So here's more of an illustration of Q-dict. So if you have a frame here, then you can look at the phonetic context, and the Q-dict includes the 3 phones before and 3 phones after. So essentially, you know, for those of us who have a lot of experiences learning a second language, when I first watched English movies a long time ago, I actually cannot catch all the words, but if there are subtitles, you know, then I can actually catch all the phone segments in the audio. So the Q-dict sort of plays that role in this process. So now we have this multi-distribution DNNs, which was originally used by my former student Shi Kang in speech synthesis, but now we use it for incorporating the acoustic features and also the Q-dict to get the phone state posteriors. Okay, so now the objective function in Viterbi decoding, we replace the ERNs, which look like this, with the free-phone recognition, which look like this, and now with the acoustic phonetic model, which call this the APM, okay? And here's the results, right? So the extended recognition network was at this level of detection and diagnostics accuracy, and then free-phone decoding has improvement. We see much more improvement in diagnosis accuracy, and APM is much better in both measures. And this work was published in the Transactions in January 2017. And recently, we actually started trying to improve further, so we wanted to incorporate articulatory features to provide complementary information of CF, acoustic, and phonological features. After all, we're talking about speech productions. So we actually referenced the work by Tepperman and Narayana, and we use the 8 streams of articulatory features, each with different cardinalities. And then with the phones, we can then generate, with the phone state, so there's a certain level of dynamics in it, we can generate this representation in terms of the articulatory feature streams. Then we apply multitask learning to the APM. So now we train not only the phone state posteriors, but we also train the class probabilities for 8 articulatory streams. Our first pilot experiments focused on the Cantonese subset of the Chloe corpus, and we found that this multitask network can actually predict the articulatory features quite well. All of these are above 90%, well above 90%. And furthermore, this is our initial set of results. The numbers are not directly comparable, but they should be a useful reference. So you can see that with the multitask APM, the detection accuracy continued to rise, and with a slight decline in the diagnosis accuracy. So this work was just published earlier this year in ICMU. Now, so my former students, Dr. Li Kun and Dr. Li Fa Xun, they actually went ahead and founded SpeechX. Actually, you may wish to visit the SpeechX booth here, S9, and this is the, so they have integrated some of the work into WeChat. And so this is a demo based on WeChat. So now you can actually do phoneme-based training.
Sit. Seat.
Okay, so the learner was not doing too well at first, and we tried.
Sit.
Okay, a bit better.
He goes to school on foot.
So there are 8 exercises based on sentences.
He goes to school on foot.
We use a text-to-speech synthesizer with the phoneme sequence and also the timing information. And we actually have these sketches of the different viseme components which correspond to the different articulators, articulatory organs. So according to the phones, we have the target frames for every articulator. And when we have the missing key frames, then we just use interpolation and generate and fill in all the frames. Then we put all these frames together, and then you can see the entire viseme being generated. So just to illustrate, we use a viseme blending technique. So for example, I pick the diphthong ow because it has the transition from a to u. And so if you start with the viseme, and this is over time. Okay, so if you start, then the viseme looks like this, and you go into the peak region of the a, and then you start to blend with the u, and then here's the peak region of the u, and then it will blend with the next phoneme. So this is how we do visual speech synthesis, but we want to do exaggeration as well. So this was a paper we published in ICASS 2013. So we build extra levels of exaggeration. So as you can see, we select certain articulatory features that are much more visible, the open, round, and bilabial features, and we create extra levels of movement range. And furthermore, for exaggeration, we want the viseme to stay in the peak level for a longer period of time. So therefore, we move to a cosine function in the blending. So whereas in the non-exaggerated regions, we'll continue to use linear blending. So here's the outcome. So for example, if you look at the word farmer, so the neutral rendition looks like this.
Farmer.
Okay, again.
Farmer.
And the exaggerated version looks like this.
Farmer. Farmer. Farmer.
Okay, so if you want to look at shoes, then the neutral version looks like this.
Shoes. Shoes. Shoes.
Okay, and the exaggerated version looks like this.
Shoes. Shoes.
Okay, so that's how we do visual speech synthesis. Now, next we want to do audio exaggeration, emphatic speech synthesis. This is where we need to analyze the prosodic differences between neutral and emphatic counterparts. So what we did was to classify phones based on their position relative to the stress syllable in the emphasized word. So we have 6 classes. We look at the phones in the stress syllable of the emphasized word, before that or after that. And we also look at phones in the word before the emphasized word or after. Okay, and then class 6 is all the other phones. Now, the challenge in emphatic speech synthesis is data sparsity, because generally, you don't have emphatic speech all the time, and even if you have an utterance of emphatic speech, you only have a very few segments which are emphasized. So to this end, we've devised 2 approaches for emphatic speech synthesis. One is HMM-based perturbation, and the other is end-to-end. Now, for HMM-based perturbation model, basically what we did was to construct a general decision tree using a neutral corpus, which we have a lot more data, and general questions that are not related to emphasis. Then we try to grow the tree leaves with phones from the emphatic speech corpus, which we collected, and classify them according to the emphasis-related questions. Then in HMM selection, we devised a cost function based on F0 and duration statistics to select the HMMs. And in the case of sparse data or missing data, where we need to substitute for the desired emphatic category with the closest approximation, we also incorporated a compensation model using based on F0 and duration. And so this is what the HMM-based perturbation model sounds like. For it is a table.
It is a table. It is a table.
Okay. Then we moved on to end-to-end framework. So this work is just published earlier this year, led by Dr. Zhiyong Wu. So the challenge is that we want to relax the requirement of paired neutral and emphatic speech recordings for the speaker. And we will also want to seek to enable control of different emphasis levels. So we have a small corpus of neutral and emphatic recordings from the source speaker, which is about 700 utterances. And the emphasis-related acoustic differences are modeled by the decoder and the attention module, corresponding to the emphasis-related linguistic differences captured in the encoder memory. And the speaker-related acoustic differences can then be modeled by the decoder and attention module with the aid of speaker embedding codes. And with this design, the emphasis-related acoustic differences can be transferred from the speaker S, the source speaker, into the speaker L, the learner, so that we can generate emphatic speech with speaker L's voice given emphatic character sequence input. So basically, during synthesis, then what we did is to have the emphasis strength control take effect by tuning the encoder memory with an interpolation factor, and that factor is fed into the re-represented memory, which is then fed into the attention module. So this is where you can see the interpolation takes place, okay? And I want to first play for you the recordings from speaker S, the source speaker. So these are contrastive, neutral, and emphasized recordings for the input text, where we want to emphasize candidates and consolidated, those 2 words. So this is a neutral recording.
A number of candidates have consolidated their accommodation with investigation and appreciation.
And this is the emphasized recording.
A number of candidates have consolidated their accommodation with investigation and appreciation.
So now with emphasis level control, we can have this alpha that we can tune. And this is a synthesizer generated based on the Nancy corpus from Blizzard Challenge. So this is, I'm going to play for you the leftmost one, which is where alpha is set to 0.
A number of candidates have consolidated their accommodation with investigation and appreciation.
And this is for alpha at 0.4.
A number of candidates have consolidated their accommodation with investigation and appreciation.
And then alpha at 0.8.
A number of candidates have consolidated their accommodation with investigation and appreciation.
And alpha at 1.0.
A number of candidates have consolidated their accommodation with investigation and appreciation.
So just to verify what we are doing, during testing, we also examined the encoder memory, the activation value of the encoder memory's difference between the emphatic memory and the neutral memory. And we find that by and large, they correspond sort of to our manually defined, the 6 classes that have been manually defined, right? So I illustrate them in red. So we want to further conduct research in this area for emphatic speech synthesis. Now, this is actually a demo of a system. Basically, we try to integrate different versions of those components that are presented in our lab. So a student can type in a sentence that he wishes to practice on.
The interest rate is rising.
And then speak that. And then the system comes back with a diagnosis, so flagging the errors in red, and the student can then select individual words and compare the model's production with his own production, and then look at the visual feedback. I should say bimodal feedback of that word. Now, this is a side project. I figured it might be fun to include. This is actually a undergraduate bachelor's thesis project by Wang Hao. It's called Music Speak. This is where we want to help our learners acquire stress time rhythm in English, which is rather different from syllable time rhythm in Chinese. So the idea is very simple. The learner can first type in any sentence in English, and then the system just comes back with a beat.
She opened the book and a box of tools.
So the learner can then follow the beat and practice. And here's another sentence as an example.
I suppose that I was hoping to prove them all wrong.
So then the student actually engaged some of his classmates and asked his classmates to record a sentence before.
I suppose that I was hoping to prove them all
And then
wrong.
each student then practiced 5 times with the rhythm, and this is what they end up with.
I suppose that I was hoping to prove them all wrong.
So basically, it's a fun project. Actually, Wang Hao has, this was his bachelor's thesis project. He has recently graduated with a PhD, not on this topic though, and he's working at Alibaba in Singapore. So I'm done with our work, presenting our work on language learning, and I would wish to now move to well-being. So we actually got into well-being not too long ago because of a need in Hong Kong for AAC, augmentative and alternative communication. So our hospital authority has been working on this, and according to our census department, it was found that nearly 5,000 people in Hong Kong have speech difficulty, and over 40% of that have no verbal communication at all. So the hospital authority has published this traditional communication book. Okay, so I'm going to play for you what this book looks like. So it has indices on the right and with different categories, and in each category there will be different pictures of showing the items in that category. Now, the limitations of this, as you can see, this book is published on laminated paper, it's difficult to personalize, it's expensive to print and distribute. So there was a need for us to help to develop the e-version of the communication book. So what we want to do is to use the iPad or a smart tablet to personalize the content and layout. And we also inject our own homegrown Cantonese text-to-speech synthesis technology into the book. And then we also collaborated with Microsoft and injected and incorporated the Microsoft Cognitive Services. So now the e-commu book can work for 20+ gender-specific accented voices. So this is our implementation of the e-commu book. So you can see that we try to preserve all the affordances of the paper version with the categories and the items. And the user can also personalize, so adding, just easily adding a picture and adding a description of the picture, and then it will go to our TTS in the cloud and come back with a page, the addition, and then from then on, the user can select it. So there are also other features that allow the user to customize the book based on his or her needs. Okay, so what we want to do then is to be able to personalize the book, especially using the voice characteristics of the user. So here, in fact, we can also do the same thing for language learning systems. In the corrective feedback we generate, especially on the audio side, we can also use voice conversion to convert it into the learner's voice color. So, this also applies to language learning as well. But now I wish to talk about it in the context of AAC. So basically, voice conversion, as many of you know already, is to modify the speech signal uttered by a source speaker to sound as if it was uttered by a target speaker. So the traditional approach is really to learn this feature mapping, this function f, from aligned parallel data. And in ICAST 2015, my former student, Dr. Li Fa-Xun, he published a paper that used deep bidirectional long short-term memory based on recurrent neural networks for the task, and it worked reasonably well. However, parallel data is often unavailable. So what do we do? So later, in the following year, Li Fa published another paper where he used phonetic posterior-grams to offer a speaker-normalized representation of the articulation of sounds so that it serves as a very good bridge between the source and target speaker's recordings. So this mitigates the need for parallel data and achieves cross-gender and cross-language voice conversion. So the system is illustrated here, and I want to play for you some of the outputs of the system. So if you look at the table, the first row, call an ambulance for medical assistance. I serve as a source, so this is my recording.
Call an ambulance for medical assistance.
So we got some speech data from the target speaker.
重新归零，然后从头开始。
Okay, and this is the conversion output.
Call an ambulance for medical assistance.
Okay, so just to give you a sense of how it sounds for cross-gender, this is Li Fa.
Hello, 你好，我是玲玲。
Again, we have the target.
重新归零，然后从头开始。
And this is the conversion output.
Hello, 你好，我是玲玲。
Okay, so this is the PPG approach for voice conversion. Now, this is okay if we were doing language learning. However, if we want to serve the people with speech disorders, oftentimes it's very difficult to get a lot of data from them. And so we needed to reduce the need for data in our approach. And this is a paper that Song Xiangliu, my student, just presented here in Interspeech 2018 a few days ago. So this is where his approach actually adds speaker embedding into the picture. So this is a multi-speaker voice conversion model that you can borrow other speakers' recordings, and also you train up a speaker embedding. And then using the speaker embedding, you can also train up a speaker encoder. So when you actually come to the need for a voice conversion for a target speaker for whom you only have very little data, such as a single target speaker utterance, then you can feed that into the speaker encoder to get the speaker embedding, and that speaker embedding can enrich the mapping to generate the target speech for conversion. So just to play for you the output of this approach, so let's say we want to synthesize someone counting. Okay, so this is 1, 2, 3, 4, 5, and then we have the source, that sounds like this.
1, 2, 3, 4, 5, 6.
Okay, so this can be synthesized. But let's say we have a target, and this target is a dysarthric speaker.
Phải mãi phóng bảo của mà bôn phải phá.
So we only have one utterance from the dysarthric speaker, especially because it takes them a lot of effort to speak an utterance. So then we can convert any source recording into to carry the voice color of this speaker.
1, 2, 3, 4, 5, 6.
Okay, so this is the status of the voice conversion work here. Now, again, on well-being, I want to move on to dysarthric speech recognition. I already talked a little bit about dysarthria. It is a speech disorder associated with neuromotor conditions and many possible causes such as stroke, cerebral palsy, Huntington's disease. And basically, it affects speech intelligibility, such as imprecise articulation, hoarse phonation, improper prosody, lengthening and slow speaking rates, excessive nasalization, etc. So we want to build dysarthric ASR as an assistive technology to help communication. In fact, one of our plan is this is together with Professor Andrew Liu, my colleague. Our plan is, if we are able to do a good job recognizing dysarthric speech well, then we can figure out what the subject wishes to say, and then we can synthesize with normal speech, and then we can convert the synthetic outputs to carry the voice color of the subject. So this is our plan. But we're really new to this work, and so we have been following the work at Sheffield, Heidi Christensen's papers and her colleagues. And so over the years, we were also trying to conduct experiments using UA speech, and I thank Mark Hasegawa-Johnson for that, providing us with that data. And so we actually published a paper this conference where Zhangwei Yu, he was able to use the following technique to reduce the word error rate to 30.6%, which is about a 12% relative improvement over the best published result from a few years back, 2015. And so the technique we use is actually rather standard. It's stacked DNN, where we have bottleneck features. We have bottleneck features, and these feed into the stacked hybrid system, and we can actually swap in different kinds of DNNs here, and you can see the different kinds of DNNs in the table with the different word error rates. Okay. Now, then we further applied cross-adaptation. And this is where we want to bring in other normal speech. So we want to bring in switchboard or broadcast news. And so the bottleneck features go through MLLR for cross-adaptation. And you can see that with cross-adaptation, the word error rate actually can make a very good improvement. Then we put everything into the pot. So this is the system combination result. And eventually we got 30.6% word error rate. And so this is English dysarthric speech, but we actually do want to work on Cantonese or Chinese dysarthric speech. So we have begun to design a dysarthric speech corpus, and we started collecting it and did some initial work on it. We work with patients' associations. We work with our colleagues or speech therapists in the Hong Kong Hospital Authority. And also we reference the French dysarthric assessment tests in designing our Cantonese dysarthric speech corpus, which we call CU-DYS. And furthermore, we have done some initial research in articulation, in studying articulation, and we referenced the distinctive feature articulation, which was from Professor Kenneth Stevens. And basically for our corpus, we invite some linguistic students to label the phone so that from this we will be able to tell for what kinds of distinctive features the subject has made errors in the dysarthric production. And furthermore, we have built distinctive feature detectors using multilayer perceptrons, and these can automatically come up with the distinctive feature errors also from the dysarthric productions. Now, generally, we find that the error flagged by the MLP is much greater than the error coming from the human labeling, and a lot of the times it's because the dysarthric production has a very weak production, and so the human does not cannot really hear it, but the detectors are able to detect it, and so that those count as substitution errors in terms of the distinctive feature errors. But in general, we find that the errors flagged by the MLP correlates well with the errors coming from the human label, so at a correlation level of 0.87. And furthermore, we can also examine for each subject the whole spectrum of DF errors, the distinctive feature errors. So here S014 male, he has a lower intelligibility, whereas S003 has a higher intelligibility. And in general, you can see that the error rates are different. And in fact, we believe that being able to flag these can indicate the articulatory characteristics that are more problematic for individual speakers, and this may inform our speech therapists in the design of intervention exercises. So that's a summary of our work so far along the lines of well-being. We have some other ongoing work which are not directly related to speech. One is more on language than speech. This is a collaboration with my colleague in public health. And this is where we actually look at language, how to better use Twitter to find a person who got lost due to dementia. And in particular, we're studying features of Twitter messages that can lead to successful search of this lost demented person. And also, our work with our geriatricians, we published a paper at KDD earlier this year where we tried to predict Alzheimer's disease with actigraphy data. So actigraphy is a watch that can actually register daily activities, motions and especially. And we have over 1,000 elderly subjects wearing this actigraphy for a period. And using that data, so based on the activity, we were able to generate circadian rhythms. And